Excellent. So thanks for the opportunity to speak here. Quite looking forward to telling you a little bit about the journey we've been on and the tools that we're developing. But first off, what I wanted to reflect on briefly was the journey that might go on within an organization in order to try and effect a digital transformation or some kind of transformation to the science that is possible for us to do. And I think it's a reality in a lot of organizations that the timelines that you have for budgeting, for assessment of whether a project's working or not, don't necessarily fit with the timelines that are required to actually roll out an effective transformation across an organization. So whenever you have an example like we've just seen where people have successfully pushed this through, then that's not just a digital and technological win, it's a massive kind of win of being able to align people for the sustained period of time that it needs to actually affect that change. So I think one of the things that's actually been a barrier to us being able to make progress in this area, I mean, it's partly the technology and the fact that these technologies are emerging and starting to come to fruition, but it's also partly about just the realities of trying to bring things to bear. I'll come back to this in a bit. First off, I want to talk to you about the transformation that we've seen starting to happen. And unlike the last talk, we're not talking about manufacturing, we're talking about right the other end of the process, particularly in drug discovery. And what we're talking about here is mostly about the experiments that we run in R&D and how we can transform those with digital innovation and automation. And actually there's kind of a triumvirate of different things, and each of these is pretty interesting by itself, but it's where these things come together that we see the real dramatic shifts, and we've seen this at our clients just in the last sort of couple of years or so. It's been really exciting to see. And these different areas are the digital tools, what we call Automation 2.0, and I will explain that. It's not just a buzzword. Well, it's a bit of a buzzword, but there is something behind it as well. And then also something that actually isn't a technology, it's kind of a methodology, which is experimental design, but it's still absolutely essential for seeing the level of impact that we've seen. So we'll start off with digital tools. And I wanted to start off with a bit of a contrast. So if we think about the sort of really classic way that we might be doing experiments in the lab, then we're asking the scientists to design, plan, run their experiments, to structure the data, and then to analyze those data to get some insight. And then on top of this, we're asking them to forensically record everything they've done, hopefully in a kind of standardized data structure, so that then actually the organization can make broader use of this, and that's often into an ELN or similar type of software. Now, what I've been arguing is that this actually presents a real sort of conflict of motivation, right? For the scientist, they want to do this bottom bit and get to their insight as rapidly as they can so they can push their discovery program forward and then get on to the next experiment. For the organization and for a lot of people in the room, well, we want them to be then recording everything as well so that we can then make future use of those data, again, like we just heard in the last talk. But the problem is they'll only ever see this as a burden, and it's a really tough burden. To make sure that things are properly written up. It's not an easy thing. We're asking our scientists to be like highly sophisticated technical writers and pay continual heed to exactly how they're recording their data. So what we'd propose is that we can flip this the other way up. So if you have digital tools which actually help the scientist through each part of the problem, there's loads of mundane and challenging things through pretty much every part of the experimental process that digital tools should and can help with. And so if you're actually helping the scientist do their experiments better in the digital world, then all of that experimental activity which happens in those digital tools can also be recording every aspect of the experiment as you go along for free, essentially. So it's flipping the whole concept on its head, and it's taking the burden of recording everything in the digital world away from the scientist and onto the digital tools that are helping that scientist to run their experiments. it probably won't be of much surprise that, you know, I'm not just using this as a philosophical argument. It's because actually this is what we built at Synthace. So we've built tools that cloud-based tools that allow you to design experiments in an abstract way. The system then has a planner which converts that high-level design into all of the low-level details of exactly how to run that experiment, down to every last liquid handling step. It's essentially simulating what the experiment will be when it gets into the lab. So it's not simulating the biology, it's simulating the experiment. And then you have a preview. The scientist, still on the cloud application, you know, at their desk, can then view all of the steps that are going to happen in order to carry out that experiment. And then you can send that to automation in the lab. It gets executed on that automation, so the platform is generating those automation instructions. And then you can pull the data from that experiment and put it in the context of all that metadata that's just been gathered from the scientist when they've been designing the experiment, but also generated by the platform when it's made all of those detailed instructions. All of this is incredibly rich metadata. And so then that means that you can very rapidly get to the insight that you want as a scientist, and we have all of that highly structured data that can then be used by the organization. And, you know, because it's a cloud-based system, this is then something, you know, I can easily just jump in and see what all my colleagues are doing. So what the design looks like is a drag and drop GUI interface. So it's essentially you have the different steps that you might want to carry out in your experiment, and you can link together samples going from one to the next, data going from one to the next, in a fairly sort of standard workflow kind of metaphor. But this isn't just a nice kind of GUI, it's also, fundamentally, it's an abstraction. It means that instead of the scientist having to worry about every tiny detail of their experiment, they can think at a higher level. They can think more at the level of science as opposed to the level of technical detail of all the liquid handling transfers and how to program the automation to do those liquid handling transfers. This then gets converted into the liquid handling instructions that are required to run that experiment. So this is a clip of our preview view, where, yeah, you can see like all the liquids being moved around, plates being moved around on a deck as it's carrying out a particular experiment. That can then be run in the lab, and actually it can be run either on automation or manually. And then you then have the benefits of all of this metadata data coming together. So we know what's in every single well that's just gone into that plate reader that's produced that CSV file. So we know what every data point in that CSV file, the full history of exactly how that data point's been generated. And that means that you can immediately produce like useful structured data views, which means that the scientist can get insight quicker, but it also means that that data set is now robust. Without metadata, data loses value the moment it leads to the scientist. Like, because that data no longer has any context. All that context was in the scientist's head, which is why we demand that they type it all down into an ELN. But if we have that data and metadata joined at the point of creation, then we have a robust data set that can then go into other parts of the organization. So what it looks like when we're looking at an experiment within the platform. So when I want to see what my folks are doing in our lab, then I can see every single step that they've done, and I can dive into each of these. So this is actually just the bottom of an experiment. I've left the bottom of the slide free so that I can zoom into various bits of this. So there were 4 different kind of processes that were done as part of this experiment, and it's created a set of digital assets that then I can just navigate and dive into in order to explore what my scientists have been doing. So in the first instance, here's the planner. Right, but this is now a planner that not just has these steps that have been put together, but it also has explanation of what each grouping of blocks is doing. So again, a higher level of abstraction. And so it's essentially the write-up now. Yes, there is still some write-up here, but it's more of a commenting on all of the details that are already there, rather than having to record all of the details and the comments. So for those of you who are more familiar with the sort of digital world, this is just like commenting your code, right? All of the actual substance is already there. And then if we go further along in this particular asset, then you can dive into the preview. You know, that wasn't just used before someone ran something in the lab for them to help them to understand what's going on in the lab. It's also the map of everything that went on in that particular experiment. So if I want to see the details of, oh, hang on, this sample looks a bit weird, like, where did that actually come from in the workflow? Oh, hang on, all these samples have that stock in common. You know, we can see all of these, we have the full map. And so once again, that means that we can then get a view on the structured data very rapidly. Essentially, we end up with these very big data tables with all the metadata and data in there, and so you can then plot whichever metadata you want to choose against the data that you want to choose. Okay, digital tools. So what this also leads to is this concept of automation 2.0, and automation is a bit of a tricky concept in a lot of ways, because we're used to what we've used automation for in the past. You know, where it takes a long time to program, where it means that if we are going to get ROI on that effort, then we need to be using that automation, that protocol over and over and over and over again. We only use it for protocols where we're going to be using that protocol extensively, otherwise there's no point. But what the abstraction that I've just shown you allows is much more rapid programming of automation. So the classic view in our heads of automation is something like a car production line. You know, if you Google now what automation means, it tends to say, oh, it's the replacement of a human's work with a machine. That's essentially what it is. So we have this idea of like a car production line and all the benefits that come from that, right? Of throughput, you know, the fact that you can walk away from it, the quality and the traceability, these are all really helpful. But I would like to offer a slightly different image of what the automation in the future could be when we can use this power of abstraction to much more dynamically use it. And that's one of Iron Man. And that's partly because I'm a nerd, right? So I like to put up pictures of superheroes. But it's also because I think it is really a helpful analogy. So in this case, you have Tony Stark. He's a human, right? And he's made into a superhero by getting into the automation, by getting into his technology, right? So in this analogy, the scientist is Tony Stark, and we can use automation to augment their capability within the lab in order that they can then do stuff with much greater dynamism and complexity than they can do by hand. Automation is really good at doing some stuff which humans just simply can't. Try pipetting into a 1536 well plate as a human. It's just, you know, impossible to handle that kind of complexity and also the volumes involved. And so what this then leads to is something quite profound, and it's enabling experiments that were previously impossible, because we have the combination of the scientists coming up with the experiments that they need to address biological complexity, then with the tools that enable them to actually do those experiments. I'm going to go into that a little bit more, and for that I need to turn to my last circle, which is experiment design. So this is something which at Synthace we've been passionate about since the very beginning, and that is that we need to be experimenting in the right way that actually addresses biological complexity. So if we think about a landscape that we're looking to explore, and I mean we can only show a two-dimensional landscape here, but like for any given biological landscape, it's going to be an n-dimensional hyperspace that we're trying to explore in an effective way. And the way that most scientists do that is they think, of all of these hundreds of different things that I could potentially investigate, I need to choose one, and I'm going to hold everything else constant, and I'm going to look at that one. That is the typical way that we do science. This is the way we're all taught the scientific method as we're coming through school. But when you actually look at like what that looks like within a multidimensional landscape, it's like a small cross-section through that landscape, and it gives us a very limited idea of what's actually going on. And worse than that, it can lead us to false conclusions. Because in this case, if we investigated these two factors in a systematic and robust way, using one factor at a time, we would completely miss the higher optimum that's actually within this landscape. So you can move from that to concepts like multidimensional experimentation, often known as design of experiments. And essentially what that allows is the walking through multidimensional space in a much more systematic way. Now, both of these methods require iteration. They require you to be doing, you know, carefully run experiments going from one to the next very rapidly. Now, or as rapidly as you can. So they, like, at least in this case, you've got to the right answer, right? Because you're actually navigating the multidimensional space a lot more effectively. But what we've seen by combining the digital tools with the automation, you know, programmed in a much more dynamic way, and then taking these concepts of multidimensional runs as well, it means that we can now apply way more experimental runs using Automation 2.0 and the digital tools than previously was possible with this type of experimentation. So instead of having to iterate, what we've noticed at our clients is that they can basically just characterize the entire space in one hit. And that sounds like it's overstating it, but we've actually seen the data. And so instead of a program taking many weeks to get to a conclusion, it's just a single experiment, and actually you get to a much more robust data set than you would have got to previously. So we've seen this in particular at AstraZeneca. So they stood up with me at SLAS Europe and spoke about the results that they had from rolling this out within assay development for drug discovery. So assays are absolutely fundamental to drug discovery. They're fundamental to pretty much all of science, for all that matter. Without an assay, you can't measure anything, right? You have no window into the world that you're trying to work with. And the assays within drug discovery have huge demands on them. They need to have a fantastic quality of signal to noise. They might be run 2 million times if they're going to be used for high throughput screening. And how many false positives are you going to get just by sheer random chance if your signal to noise is poor and you're running something 2 million times? It's going to be tons. And they'll often have to be reproducible over 4 years of actually, or more, of actually running those early preclinical studies. So the demands are huge, and actually the complexity of them is going up. We're going from simple enzymatic or binding assays all the way through to cell-based assays and multicellular assays, organoid-based assays. And so the challenges to these teams are massive. And so what we found is with the experiment platform, because they could do this scale and ambition of experiment that they wanted to be able to do, it opened up new horizons of the kind of experiments that they thought were possible. And it meant that they were developing assays in weeks instead of months. Or instead of 5 experiments, it took 2 or 1. So that's just reducing the amount of time on the critical path to discovering new drugs. Which, so here we have a digital tool that's having impact almost the moment that it's being used for like the first experiments it's being used within an organization. And the assays were of higher quality. They had, if you're from that space, better Z prime, which is the ludicrously rigorous measure they use for signal to noise in that space. They had larger assay window, greater robustness. So what that means is less rework. It means like when you're actually using that assay, you don't have to keep going back and redoing things in order to try and actually get convincing results from your drug discovery process. So the effect is that drug discovery time overall is improved by weeks to months. Frankly, we don't know the exact amount of time that it's improved by because this is relatively new stuff and we haven't tracked these all the way through the drug discovery process yet. I want to go back to the journey. So if we're thinking about digital transformation and the digital tools that we might want to use, we need to be able to show value quickly, or ideally, we need to be able to show value quickly. And what we're really excited about is that these are digital tools which we think are profoundly helpful and could be helpful across an organization, but you have a really clear start point which will deliver significant value which is recognized by any drug discovery organization. If you could take time off the time it takes to get a drug to market, that is something which anybody's going to be able to argue for within the organization who's passionate about digital change. And with that, I'll end and I'll open it up to questions. Thank you.
Thank you, Markus. The floor is open for questions.
Yeah, thanks. So I was wondering, that clients might already have systems in place, benchling, for instance. They have lab notebook templates installed. Does your platform replace it or use it?
So at the moment, it's all about working within the digital ecosystem that there is. I say at the moment because it's an interesting thing then to extrapolate a little bit and to think, okay, well, if we're ending up with something that's automatically recording everything, like, you know, we don't have, you know, all the reporting functions that you might want from an ELN, or you know, a lot of things that we heard about that are valuable in later parts, of more regulated parts at this point. You know, the digital platform is pretty much what I've showed you. And so that means that for all those functions, you know, we look to integrate with all of the other digital tools. And, you know, our philosophy is one of an open stack, right? So we are focused in on the experiment. You know, we call ourselves an experiment platform because we're not quite sure what else to call ourselves, because nobody's done something like this before. But we're not even vaguely arrogant enough to think that we can do it all. And so absolutely we look to integrate with, you know, the existing digital ecosystem that's out there. Yes.
How diverse? How many different robots?
So we, in the assay development example, they primarily use dispensers, and so we cover all of the dispensers that are used in that area. So they're, you know, Echo, Dragonfly, Synthace Flex, another that's currently slipped my mind. And then in terms of the larger kind of liquid handling platforms, it's things like Tecan Evo, Tecan Fluent, Hamilton Star, and Starlet. Is what we've covered thus far. It's an interesting one, that, because when you say that you integrate a system that's that flexible, then actually what you're saying is you integrate a whole ecosystem of different possible configurations that that tool might have. So the reality of it is that we integrate, like, you know, a much used subset of all the different configurations that system might have. And you know, the automation is kind of a powerful component of what's happening here. But, like, fundamentally, I think that digital spine of everything that's going on, like the example that I had up there where one of my lab members had done that experiment, he had 4 separate steps. One of them was automated and the rest were manual. Because I think this is the reality of a lot of lab work. You know, you use automation for where it's most powerful, and then you're still doing manual processes around, but you want to be able to track them all.
I have a question, Markus, also regarding a little bit about data standards and such.
Yeah.
Because also we heard from the previous talk about this integration layer of data and systems, and I still feel that a lot of companies are trying to solve it all. You say you want to specialize, and how much do you push for open standards, and what kind of, for example, your pipetting language, is that an open standard that can be exported into some markup language, or how does that look like?
So at the moment, there hasn't been any standard that's tried to address the level of granularity that we have for automation. So that is our own language that we use sort of under the hood, if you like, that defines each of those blocks that you see being dragged around. Early in the company, we actually looked to have people coding their own blocks, and then we found at that point there was very little demand for that, and it was also, you know, so we moved more to that sort of abstraction. But there's absolutely no fundamental reason why we might not open that back up again as we move forward, so people can then develop their own blocks going forward. You know, it's like, I'll just be honest, like, it's a really tough journey to try and make, you know, something of this sort of level of interconnectedness, if you like. And so we kind of have to choose which thing we bite off as we go. But what we found really successful is when there are customers who have an aligned vision with what we're looking to do, of what that future might look like, and then go on that journey together, right? I think that's absolutely essential for making the right kind of innovations in this space, and we've found it to work really well with our existing customers to date. Sorry, was that too fluffy answer, or did that?
It was all right.
Okay.